Next up is Arushi Nath with Constraining Exoplanet Mass and Orbital Period from Transit Timing Variations using N-Body Simulations. I almost had that memorized.
Thank you so much, Tom. Hello, everyone. It's wonderful to be here. My name's Arushi, and today I'll be talking about constraining exoplanetary mass and orbital period using N-body simulations. So let's get started. So first, let's look at an exoplanet system. So here's a short animation. So here you can see there is a globe in the center, the star, and you can see there's a planet orbiting around it because of their mutual gravitation. As the planet goes in front of the star, there's a short dip in light observed as the planet blocks a part of the star's light. This you can also see as the planet goes behind, it'll come in front again, and this dip in light will be repeated. And this dip in light will happen at the same time each time. So let's say if the set interval is an orbital period is 10 days, every 10 days you will see the same dip in light happen. But let's complicate it a little bit. What if there's more than one planet? What if, let's say, there's two planets? Now, there's not only the gravitational pull between the planet and the star, but there's also the gravitational pull in between the two planets themselves. And that creates changes in the transit timing of the planet. So now, let's look at these two examples of when the transit may occur earlier or later. In the first figure, you can see the transiting planet is the inner one, the one we're looking at. Here, the planet is behind the other the other planet, which means the outer planet is pulling it forward. Therefore, the transit would happen earlier than expected. However, the opposite can also happen. Let's say the transiting planet is in front of the perturbing planet. Then, the other planet will pull it backwards, and the transit will happen later than expected. So here, we can see that the transit timing is not consistent. So what happens if we plot these transits? Each time there's a transit, we see the exact timing, the mid-transit timing of the transit. And we do this for, let's say, 9 different transits. Then you will see different shifts in the mid-transit timing. And these timings is called transit timing variations. And you can see a little plot about that on the right. So why are these transit timings so important? Well, these transit timings allow you to detect new exoplanets. Let's say you have a system in where you only know one of the planets. You can see it transiting, and then by measuring the transit over hundreds of orbits, you can see that the transit is shifting in a continuous way. You will be able to predict that there may be another planet in the system. And so far, 32 exoplanets have actually been discovered through this method. So, my project has 2 main goals. First, generate thousands of N-body simulations that accurately model these gravitational interactions between planets. Second, use these N-body simulations to be able to constrain the mass of the unknown planet in the system. And this is really useful for actually exoplanet systems where one of the planets may not be transiting because they're above or below the plane. And this allows us to be able to detect exoplanets we could never have done before. So how did I make my N-body simulations? So these simulations use 13 parameters. First, you need to know the mass of the star. And you also need to know the 6 orbital parameters of both planets: their mass, orbital period or semi-major axis, eccentricity, inclination, and argument of pure astron. And using all of these parameters, if you input them into a simulation, you'd be able to figure out what the transit timing variations of one of the planets would be. So to create these simulations, I used a modified version of Rebound's IES 15 integrator. So here are the constraints I set for each of the parameters. So to set these constraints, I went on the Exoplanet Archive website, and first I looked at the 32 known exoplanets that have been discovered through the TTV method, and I basically plotted their distributions to see where most of the parameters lie. Using this, I constrained the parameters. For example, for the transiting planet, so the planet we're able to observe, I constrained its mass to 0.5 to 20 Earth masses. And for the perturbing planet, so a planet that may not be transiting, I constrained it to 0.5 to 320 Earth masses. And I did the same for orbital period, eccentricity, inclination, and argument of pure astron. And I run thousands of simulations ranging over several weeks. But how exactly did I choose how to sample these simulations? Well, originally I went with the Gaussian approach, so completely random, picking in between my ranges stellar mass, inclination, all of the other parameters. But I soon realized this was a problem, because Gaussian distribution means it doesn't remember what it picked last time, and over thousands of simulations and such a wide parameter space, often values were clustered around, as you can see for the stellar mass, inclination, and argument of periastron in the first row. So I settled for a second approach called Latin hypercube sampling, And this approach is different. Here, depending on the number of samples you want to create, it creates a grid of parameter space. And each time, you can pick a different grid. So for the first simulation, it'll pick a number in the first grid, and then it'll remember that it picked that number, and it won't go to the same grid again. This allows it to much better sample, and the whole parameter stays evenly. As you can see in the second row, where the histogram plots show much more even across values. So now that I had my thousands of simulations, I want to create some cool plots. So here you can see a plot of the orbital period ratio on the x-axis, so this is the ratio between the two planets, and on the y-axis you can see the transit timing variations that I was talking about earlier. And you will notice something very interesting. You will see near resonance, so in the resonance 2:1 and 3:2, there's a huge spike in the amplitude of these transit timing variations. And just as a quick reminder, planets in resonance are those where basically the orbital periods are ratios of one another. For example, 2:1 resonance mean one planet, let's say the transiting planet, would do one orbit, while the outer planet would do two orbits. And it's much bigger because this is actually a log scale, so you can see the huge impact on resonance. For example, resonance, you can see it goes up to 10 to the power of 2, so 100 minutes of transit timing variation. While away from variance, it can be really, really small, like 10 or even below. And here you can see I've actually plotted this for different masses. But let's look at something different. Let's focus on these two resonances here. You will see that actually the 2:1 resonance has a much bigger spike than the 3:2 resonance. And this is because these gravitational kicks caused by the other planets are much more repeated and frequent, causing the amplitude to be much higher. And you can see I plotted this for 4 different mass values. So you can see the lower one is a mass value of 5. This is for the perturbing planet. And you can see it slowly rises up till 40. So you can see as the masses of the perturbing planet rise, the TDV amplitude rises as well. And it's shown much more clearly here. So here you can see the 3 plots, and this is centered on 2:1 resonance. So you can see on this plot right here, the mass of the perturbing planet is the lowest. And you can see as it goes higher, you can see the TTV amplitude increases a lot. And again, this is a log scale, so the increases are much more. But the same thing doesn't happen if you change the mass of the inner planet. You can see 3 different values of the inner planet mass, but all of them produce roughly the same amplitude. And this is because TTV amplitude is not based on your own planet, but it's more based on the perturbing planet. So the transiting planet has very little impact on itself, whether it's huge, whether it's small. So now I've been talking a lot about TTV amplitude, but how exactly do we calculate it? So here I have a curve of a possible TTV curve. So you can see it goes first, we can say it's about at -7. And this means that the transit was 7 minutes earlier than expected. And the next transit was, let's say, 6 minutes earlier than expected. And I plotted this for over 100 transits. And one thing, so what I did is to calculate the amplitude, I simply took the maximum transit, so the latest the transit ever was, so maybe about 8 minutes, and I took the earliest the transit ever was, so -8 minutes. And basically, I found the absolute value, looked at the amplitude, and then divided it by 2. And a larger amplitude would indicate that these perturbations are much stronger, suggesting either the planet is much more massive or it's much closer or in resonance. Next, amplitude is not the only thing we can calculate. We can also calculate the period of these curves, because as you might have noticed, they're very sinusoidal. So, to do this, I used a method called Lomskargel, which is basically fitting sinusoidal curves to this data using least square regression. And as you can see in the plot right here, I was able to find the dominant period to be 40 epochs. So what this means basically is that it takes 40 different orbits to the transit timing to go back to the original transit. And this 40 orbits is much longer than the orbital period of the planet itself, suggesting that there's a huge and strong resonance. And let's see more about that in the plot here. So here I plotted on the x-axis, delta, which is the distance of the period ratio from a resonance. So in this case, 2:1. And on the x-axis, I've plotted the period, or superperiod, as we call it. So you can see far away from resonance, the superperiod is not that big. It's about 40 epochs. But as you go much and much closer towards resonance, let's say you're 0.2 away from the period ratio of 2, it's gone up to 100. And for 2:1 resonance, the dominant period or superperiod can be up to 200 times the orbital period of the transiting planet. And let's look at that for different resonances. So here, not only have I plotted 2:1 resonance, but I've also plotted 3:1 and 3:2. And you will notice that these higher order resonances have, while they may have weaker gravitational interactions, but since 3:1, for example, will have a much longer superperiod because they're extended among much longer timescales. And here, you can see I've also plotted 3 different triangles. They're associated with real Kepler objects, so I've been able to plot their delta versus superperiod, and you can see they match very well with these plots. And let's look at an interesting case. What happens if both planets in the system are transiting? The answer is we'll be able to see transit timing variations in both planets. So each planet might have different TTV amplitudes, depending on, let's say, one of them is bigger. The bigger one will likely have a smaller TTV amplitude because it's affected by a smaller planet, while the smaller planet may have a bigger TTV amplitude. You will also notice that these TTV phases are anti-correlated, which means while one planet is transiting earlier, the other planet will be transiting later. And this is because, as we saw in one of the plots or images at the beginning, it's always the planets that are pulling each other forward and later and causing them to come earlier or later. So that means as one planet pulls the other one forward, the other will go back. So it'll be an anti-correlation. But they'll also have the same superperiod or dominant period, meaning that the period will be the same. So here is a GIF I've prepared. So you can see right here, this is delta, so this is how close it is to resonance. So it's slowly going closer to resonance. And you'll see, I hope it's big enough, but you will see that the dominant period is slowly increasing. So this is because as it goes closer to resonance, superperiod is increasing. And let's just wait a few seconds. Let's see the values here. So now you can see it in the Lomskargel. If you look at the values, they're definitely increasing. And you can even see in the first plot, you can see it's becoming much bigger. You can clearly see the different sinusoidal curves as it expands a lot. And this is as it's very, very close to the 2:1 resonance. Delta is less than 0.01. And here you can see it was the max. So now let's look at some real data. Here is Kepler 18c and d. In this system, both planets are transiting, which means it's possible to get TDV curves of both of them. So above, you can see Kepler 18c, and below Kepler 18d. You can see that they are in that anti-correlated phase, and their superperiods are about the same. And we can find the superperiods using the same sinusoidal fitting method, or Lomskargel. You can see both of them show periods of approximately 270 days. And if you look at the plots, the TTV plots, you will see that's about right. From one peak to another, it's about 270 days. And this 270 days is a huge superperiod compared to the Kepler C orbital period of about 7 days. And this shows that they are definitely in near resonant configurations. And these plots were actually generated by me. I was able to query the Kepler telescope and extract data from all of its quarters and use them and a software called Exotic to be able to create these O-C plots. So I wanted to be able to test my algorithm and n-body simulations on Kepler-18c to be able to see if I could predict the mass and orbital period of Kepler-18d. So here, I took Kepler-18c as my transiting planet and just ignored Kepler-18d transit and assumed it was the perturbing. So here, this is what I was given. Since I already knew Kepler-18c, I knew its mass was about 17 Earth masses and its orbital period about 7.5 days. And now I wanted to find about Kepler-18d. So the first step was extracting the transit data, as I mentioned before, so querying the Kepler database and being able to extract all of the transit curves and finding the mid-transit times. And I was able to calculate the amplitude and found it to be about 8.17 minutes. Then I used the Lomskargel method, so I was able to fit a sinusoidal curve, and I found super period was about 267 days, which is about 35 epochs. Epochs simply being the number of orbits of the planet. So since the epochs was so big, it was likely that it was in some sort of resonance with the other planet. So how exactly do I find the mass? Well, here I have a plot I've created of about thousands of simulations that I've ran. So on the x-axis, you can see the delta from the 2:1 resonance. So in this case, I was assuming it was a 2:1. And on the y-axis, you can see the O-C amplitude. And I've plotted this for several different mass values. So you can see 5 Earth masses, 10 Earth masses, 15 Earth masses, 20 Earth masses. And I kept the transiting to 17 Earth masses to replicate Kepler-18c. Now, I know something. I know that the amplitude, or O-C, of Kepler-18c is 8.17 minutes. So I plotted a horizontal line at 8.17 O-C amplitude. And I looked and see which points fell in this curve. And I found 8 points, all of different masses, all of different deltas. And this is where a slight degeneracy comes. There's so many different values. How do I know which one is the true delta and true mass of this exoplanet? So here I turned to super period, the second information I knew about Kepler-18c. So here's just quickly a table of all of the 8 different possibilities I had extracted from that plot. So here you can see a plot of super period versus delta. And you can see as delta increases, super period decreases. So now I already knew the super period of Kepler-18c. So if I could find the super period of all of these 8 different points I had and see which one matched the closest with Kepler-18c, I could find which was the right combination. So using these plots, I was able to create and find the super period of each of these 8. And, as you may recall earlier, I had said the super period of Kepler-18c was 35 epochs. So scanning all of these, all with very, very different epochs, I found the one which had the closest, up 32.6 epochs, and that was with an outer mass of 15 and delta of about minus 0.058. So that was the value I'd found. I'd found the mass was about 15 and the delta was minus 0.058. And using this, I could find that the period ratio would be 1.94, simply by subtracting 2 from it. And I compared my values with the NASA Exoplanet Archive and found a very good match in period ratio, delta, and mass. You can see the mass may be slightly off, but I only did at 5 Earth mass intervals. If I were to create my ISO lines my mass lines at much finer intervals, I'd be able to find a more accurate mass. So what's next? So now I want to basically create more complex n-body simulations. Because while finding the mass, I'd assumed that the eccentricity was 0. But with many planets, that's not the case. I was just lucky with Kepler-18. So I would like to also start varying the eccentricity and inclination in my plots to be able to find more accurate values. In addition, I would like to find chopping signals. So basically signals that are sometimes caused in the TGV curves. So not the main sinusoidal curve, but sometimes there's also smaller signals caused solely by the mass of the other planet, and this could help me narrow down the mass even further. And finally, I would like to expand this to include real data not just from the Kepler telescope, but also from TESS, ground-based telescopes, and even telescopes from citizen scientists. And as always, I'm always looking for more time to secure and provide telescopes to continue my research. So with that, thank you very much, and I'd be happy to answer any questions.
Thank you very much, Arushi. Any questions from the audience? No? Okay. Any questions online? No questions online. All right. Yeah. Just trying to take this all in. Wow, amazing work, Arushi. Let's just say we are all confident that this is not the first time you will be lecturing here at this university.
Thank you.
All right, ladies and gentlemen, we're going to go to... Oh, one question.
So I see you're doing your observation based on Kepler 18 C and D, but we know there are other planets in the same system. Could they have any effect on your observations, or are they too far away from the orbit to affect it?
Yeah, that's a great question. And in fact, yeah, there is another planet in the Kepler 18 system. But actually that planet is not in resonance with the other two planets. So TTV signals are often amplified when these planets are in resonance. So their period ratios are multiples of each other. But since the other planet, Kepler 18d, I believe, is in much bigger orbital period, its resonance does not match those of the other two planets, and so its impact on the TDB curve is almost zero.
All right, so we're going to go to fun facts as we set up for our next speaker.